In the recursive sets lesson, we saw this definition of this recursively defined set. And in that video, I drew out the first 3 iterations of the recursive rule and our basis step. And you can see those here. Now, one thing we might notice from these, we might see a property in these and think that that property continues for all of the entire set, no matter how many recursive rules you apply. And that property that we might see is P of t, t for trees, because these are all trees. P of t is that every vertex of t has degree 0 or 1 or 2 or 3. And in fact, that you can see that to be true for the basis step, right? This thing has degree 0, so every vertex of the graph created in the basis step has degree 0 or 1 or 2 or 3. Right? Because remember, for an OR to be true, only one of them has to be true. In this tree created here, we have, this is degree 2. These are degree 1. There and there, right? So this, you can see it's true for that tree that every vertex has degree 0 or 1 or 2 or 3. Here we have degree 2, degree 3 there, and degree 1 there, 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 and there. And you can see that this continues on with recursive rule 3. That tree created there does have, every vertex of that tree has degree 0 or 1 or 2 or 3. Okay, and so now we want to prove this property, and we'll prove it using structural induction. Every proof by induction has a base case, so our first step is the base case. And in this video, I'm just going to go through the setup, and when we get to structural induction 2, I'll prove it. I'll go through the actual proof. So for the base case, we want to prove that the thing created in the basis step, in this case a single vertex, has the property. So our base case is a single vertex has degree 0, 1, 0 or 1 or 2 or 3. All right, now the inductive step. I think of the inductive step as having 2 parts. We have the setup and then, or I guess I think of the inductive step as having 3 parts. We have the setup, we have the assumption, and then we have the proof part. But just in terms of setting it up, before we actually do any proofs, there's 2 parts, and that is the setup, what I call the setup. And the setup is basically like if you think of this as your graph T, you want to think about what had to happen to get to T. We had to take, so what we want to say, okay, if this is my T, I want to say, okay, what had to happen to get T? All right, so to get T, I had to make 2 copies of T prime, create a new vertex V, and then add an edge from V to those 2 copies. Right, remember that's how this recursive rule goes. We take whatever was created in recursive rule 1, make a copy of it, create a new vertex V, and add edges like that. That's how we get T. So the setup is, suppose T in S was created by one or more applications of the recursive rule. So in this case, in this abstract case, we're just dealing with these graphs. We have to say, okay, what does T look like? So T looks like this. T looks So this is what T looks like. T looks like this. And now our assumption is that the thing that came before in the previous recursive rule that led to the creation of T through the recursive rule, our assumption is that that thing, in this case T prime, has the property. So our inductive assumption is that the thing that came before, now let's go back up here to the specific case of recursive rule 2. Remember, this could be in any of one of these infinitely many recursive rule applications that we have here. Any of these moving over to the right here. You could think of recursive rule 4 and then recursive rule 5 and on and on and on. So we have T here. T was created by applying the recursive rule to T prime, the thing that came in recursive rule 1. And our assumption is that T prime has the property. And then we prove that T has the property. So our assumption is that every vertex in T prime has degree 0, 1, 2, or 3. And what do we want to prove? Want to show or want to prove? We want to prove that T has the property.